Of the three possible responses to an applied load, we're most interested in equilibrium. This video is going to restrict its attention to rigid body equilibrium. Remember, the difference between a particle and a rigid body is that particles can't experience moments because they don't have any extent, so there's no distance to apply a force at that causes a torque. Rigid bodies do. So the basic idea for a rigid body to remain in equilibrium is that the sum of forces has to equal 0, and the sum of moments has to equal 0. All the forces, all the torques have to add to 0. In general, we're going to experience two types of loads acting on an object: applied forces and reaction forces. And I should say applied forces and moments, and reaction forces and moments, because we can apply pure moments and pure reaction moments show up as a result. Remember that applied forces are all of the things that we typically do to a system. They're what we think of when we see the problem. So all the external loads and the weight are the applied forces. So external loads and weight are applied. Reaction forces are what the system does in response, and they're usually unseen. These are the things that act to oppose the applied forces, keeping the system in equilibrium, and we usually have to think about these a little bit because they don't necessarily show up directly in the problem statement. In general, though, reaction forces act at the location that the system attaches to the rest of the world. In other words, the mounts and the supports. And you need to know that for a rigid body, there are a huge number of options for supports. We've got pins and rollers and sliders and clevises and a million different options. So rather than trying to memorize a whole bunch of things, what we want to do is we want to interpret the drawing of each one of them by, say, chopping it off of the rest of the body and looking at that one little joint and asking, which ways does this prevent motion? Any direction that you can't move gets a reaction force. So, for example, maybe we have part of a beam, and this end of the beam is being supported by what is called a pin joint. So we've got some sort of a buckle here with a pin going through it. And if we yank on this thing, we will not be able, if I pull on it this way, we will not be able to because the pin prevents translation horizontally. And so we'll draw a reaction force for the pin in the horizontal direction. If I tried to yank up and down on this, I'd experience the same thing. And so we would draw a pin has a reaction force. On the other hand, if I tried to rotate this thing, this would act like a hinge. It would rotate freely, and so we do not draw a reaction moment for this particular joint. Another joint that you'll see quite frequently is a roller. So here's a roller. It's like a ball or a cylinder with the object sitting on it. If I start yanking this thing around, you'll notice that I can, in fact, drag it horizontally, and so we do not get a reaction moment there. If I tried to rotate it, we're not going to get a reaction moment either. So no reaction force horizontal, no reaction moment, because I can just rock back and forth on this ball. In fact, the only thing I can't do is pull up and down on it. If I pull up and down, I'll really push down on it. This thing prevents that motion. Last example, a fixed joint. This is like if we were to take the beam and, say, weld it to the wall. Now we have a thing that if we were to yank on it, don't need to draw it again. If we were to yank on this thing, we would not be able to pull it sideways, and so we would get a reaction force horizontally. If I try to yank up and down, I wouldn't be able to move it, so I get a reaction force vertically. And now if I try to twist it, that welded joint tries to prevent it. You could also think of this as like a telephone pole stuck in the ground. We can't tip it over. There must be a reaction moment that shows up as well. So let's pause for just a minute and think about what it means to be well constrained. A well-constrained system is one that has supports And what we want to do is we want to have the minimum number of supports for the degrees of freedom. So if you think about it, we've got 3 translational and 3 rotational degrees of freedom, and we want to use the fewest number of reactions to hold all of these things in place. 2 common ones that you'll see in 2D systems, 2 common 2D support systems. I'll write that out, support systems are the cantilever beam, which is what we just drew a minute ago. It's a welded thing, so a beam jammed into a wall. It could have some applied force acting on it. And if we were to draw a free body diagram for this thing, the arrows on that diagram would include the applied load, like so, and 3 reactions: a vertical reaction, a horizontal reaction, and a reaction moment. The other common support system that we'll see is a pen and roller. Drew the ingredients for it up above, but let's draw it now as one system. Excuse me. So what we're going to have here is a pin joint on one end, a roller joint on the other, and some sort of an applied load acting on it. And the free body diagram for this pin and roller system is going to have the applied load, and we're going to have some reactions. We'll have the vertical and horizontal reaction of this pin, and we're going to have the vertical reaction of the roller. So what you see here is that the pin provides a vertical and a horizontal reaction force, and then the roller acting at a distance from the pin has the same effect as a reaction moment, but it doesn't actually create one. Instead, the support just provides a vertical force, but this creates a moment about the pin joint, which constrains the rotational degree of freedom in our system. And so instead of a reaction moment, we actually get 2 vertical reaction forces that act at a distance from each other. All right, well, first step in solving any of these equilibrium problems for rigid bodies is to draw the free body diagram. And so let's just carry on with this example of free body diagram of this thing. We need a list, right? We have the applied load. Let's name it F. Draw its arrow. We need to establish our coordinate system of X and Y so we can talk about things in the right directions. And we're going to have 2 locations that we're interested in reaction forces. So I'm going to name them. This is going to be point A. This is going to be point B. Slide up a little bit so it's easier to look at. And so now we're going to have reactions at A, and I'm just going to call them AX and AY. So we have AY and we have AX. X. We're also going to get reactions at B. Only here we only have the one reaction, right? The vertical reaction. So we'll call that BY and be done with it. Now, we're going to need a little bit of geometry, so I'm just going to go ahead and write that in. The length of our entire beam we'll call L, and the distance from A to the applied force here, F. That distance I'm going to call little d. The second step is to go ahead and write out our force and moment balances. So the second step is going to be to write out our force and moment balances. And the forces are obvious. We're going to do forces in X, sum of forces in X and Y. So forces in the X direction, we have minus AX, since I drew that to the left. And we have the horizontal component of F, which we could call F sub X, and that's positive because it acts to the right, and we'll call that 0. And then we have the sum of forces in the Y direction, the vertical direction. We have AY, which we drew going up, so it's positive. We have FY going down because the vertical component of F acts downward. And we have BY, acting up, and that better equal 0. So we need a third equation, and that's going to be the sum of moments. And the question is where? Sum of moments. We can sum moments about any point in our system that we like. A trick to remember is that the force does not create a moment about a point if its line of action goes through it. So the forces at A don't create a moment about A because their lines of action pass through A. A hack we can do to save trouble on our algebra is to pick the location to sum our moments that has the most number of forces that we don't know the answer to because they're eliminated from the moment. So it's best here to sum moments about A, sum moments about A. And so we have two forces that create a moment about A. The vertical component of F, which is going to create a clockwise rotation. So we're going to have a negative moment Fy. It acts at a moment arm distance D. And then we have a second force here, the reaction force at B, which creates one, but that's counterclockwise, so that's going to be By, and it's going to act at a distance L and be positive. At this point, we want to go ahead and move to the third step, which is, whoops, it's the bottom of my screen. That's okay, we're almost done. The third step, which is to handle our geometry. So the only thing we want to simplify here is our force, right? We need to write the force components, Fx and Fy, in terms of something we know. So we could use trig here, right? The cosine of theta is going to equal adjacent over hypotenuse, Fx over F. And so we can solve that real quick and find that Fx is just equal to F cosine theta. We can do the same thing. The sine of theta is opposite over hypotenuse, which in this case would be Fy over F, looking at that little triangle. And so we get Fy is equal to F sine of theta. And we can sub those in here. And so now what we'll get is minus Ax plus F cosine theta. In the y direction, we'll get Ay minus F sine theta plus By. And in the moment equation, we'll get minus F sine theta times D, the moment arm, plus By times L. This is where I like to do my audit. I need to have the same number of equations as unknowns, and if you count here, I have 3 equations, and my 3 unknowns, assuming they gave us the force and the angle, would be Ax, Ay, and By, so that's 3 unknowns. The fourth step now is to do algebra to answer the actual question, of what we're interested in. And this comes back to the problem statement. We can solve for any 3 unknowns given all the other information. So maybe we're looking for the support reactions, in which case we'll be looking for Ax, Ay, and By. Or, given some limit on those, we could instead be asked to find the force and the angle at which it's applied to limit that, right? So what's the maximum force we can do? We could also be asked where the best place to put it is. How long should the beam be? Or where should F be in relation to point A? These are all unknowns that we could solve for now that we have a model. The point here is sometimes we don't know reaction force, and other times we might want to find a limit for a load based on some constraint. Either way, if you follow these 4 steps to set up your system model or your solution, you'll never find yourself getting stuck solving rigid body equilibrium problems.